This next chapter is about optimization, and the title is Caterpillar Won't Be Building a Social Network. So an observation here, when more of the industrial sector, when more of the, I guess you'd say the brick and mortar and manufacturing sector and all, when they start to move towards some of the technologies that we're working with big data, machine learning, data science, et cetera, that have evolved out of, say, mostly ad tech and other areas of e-commerce, finance. But when more of the manufacturing and the real heavy equipment kind of stuff moves into that field, I doubt that they'll be building social networks. I doubt that they'll be concerned with the same kinds of things that e-commerce has been mostly concerned with. And instead, they'll be focused on optimizing very large supply chains, working on pricing strategies, maintenance schedules, very, very solid business problems, but at a kind of scale that's just immense. That's much more than what we encounter in terms of the data for, say, social networks. And part of the issue there is that when you look at manufacturing, when you look at heavy equipment and transportation and real world kinds of business, these are becoming more and more involved with Internet of Things, with large-scale sensor arrays, a lot of telemetry, and frankly, the data rates on that are orders of magnitude more than what we're currently seeing with even large social networks. So the point being that I feel there is a kind of retooling in progress, and a lot of the skills and tools that have been so useful in, say, ad tech aren't exactly the same kinds of tools for the business optimization challenges that are ahead. So I'd like to show here something called linear programming is a type of an approach towards optimization. It's very good for working with exactly those kind of problems: pricing models, supply chain, distribution, routing, things like that. Linear programming was an approach for solving a system of linear inequalities. It became quite important during World War II. It was actually both in the United States and on the Russian side, I believe also UK. At a national level, they were looking at very large problems for logistics. They had these really long supply chains of getting equipment and supplies out to the front. And this notion of mathematical optimization allowed countries to be able to handle those kind of critical things during very crucial time. Subsequently, after World War II, during 50s, 60s, 70s, et cetera, these kinds of techniques were rolled out into industry. And linear programming in particular, there was an early method for it called simplex. It became very popular. The grand idea is that you've got some function that you're trying to optimize, some objective function. And I'm going to denote it here by vector C. So we're actually looking at flipping C around. So we're taking C transpose. But we've got a function based on C. We're going to try to maximize that. And we've got a matrix A that represents the coefficients in that linear system. And then we've got a vector B that represents the other side of the inequalities. I'll show an example here in a bit. But basically, these 3 points here, maximize C or minimize C, and subject to AX is less than or equal to B, also subject to X is greater than or equal to 0. The last part's subtle. What it means is you're working with tangible objects, and the values for those can't go negative. You can't have negative airplanes or negative trains. So typically, if you're consuming resources or allocating equipment, these are going to be 0 or more. And there's some great properties for that. We can state this in terms of matrix math. We can have an objective function. We'll call it z of x, and it's going to be equal to our costs, c, vector c, times vector x. X is our variables we're trying to solve for. And then we've got what we call a feasible region, ax less than or equal to b, where x is greater than or equal to 0. The objective function, this is much like what we'd seen before. We're either trying to minimize it or maximize it. If you're looking at an objective function that is talking about costs, you probably want to minimize that. If you're looking at an objective function that's talking about revenue, you probably want to maximize that. Really, it's just a matter of flipping some of the signs around. But it's the same math. And down at the bottom of the screen here, there's a shot from Wikipedia. I definitely recommend the article there on linear programming. But you can think of this as if you had, say, 3 variables there. Looking at 3 different variables, maybe it could be, I don't know, trucking costs versus factory costs versus sales overhead. So we've got 3 variables, we want to try to optimize them, and we can state what our objective function is in terms of different intersecting planes, if you will, in that space. And the inside of where all those different planes intersect, that's going to be the part that's feasible. So what we're trying to do is move as far out to the edges as possible and find the optimal parts, find where we make the most profit or where we reduce the most cost, things like that. Okay. So the big idea here is that constraints aren't necessarily equations. If you're saying that, well, I have a fleet of 1,000 trucks, I can only allocate up to 1,000 trucks. That's not an equation, but we can use a trick to turn it into an equation. So in linear programming, there's typically use of something called slack variables. We're going to create some synthetic variables, if you will, and introduce those to change inequalities into equations. So I'll try that on the board here. Let's say that we've got 5x plus 4 is less than or equal to 20. Okay, you've got an inequality there. One of the things you could do, well, first off, let's simplify this. Let's say 5x plus 4 minus 20 is less than or equal to 0. Okay, so combining terms, minus 16 less than or equal to 0. Now, one of the other things we could do here would be to introduce another variable. We could say 5x minus 16 plus some variable y equals 0. And basically use the y to take up the slack for this less than or equals right here. And we're going to try to make sure that we handle this appropriately, but it's a way of converting a whole bunch of constraints into a linear system. So looking at the diagram here, the problem with linear programming is that you have an underdetermined system. You have n variables, but you have less than n equations. And as a result, you could have many, many different possible solutions. You want to try to pick the ones that are most optimal. So it's an underdetermined system, and we're working with optimization. And the trick here is you can start out with this basic equation, ax equals b, that kind of a matrix. Let's just say that we've got this form of a matrix we've looked at a lot before. To introduce the objective function to be maximized and to introduce the constraints, we can think of having an a and a vector x and another vector b. So that's conceptually that's the abstraction we want to work with. But what we're going to do here is actually turn a, convert it into something else. We're going to add an identity matrix. We've seen this a lot before. We're going to stick it on the side of A. Actually, let me draw it a little closer on the side. That's actually a square matrix. Maybe my drawing isn't quite square, but it is. And then we're going to take, let's see, our x's, like we had before. But we're going to add the other slack variables down here. I'll just denote that x prime. So we've got another little chunk of x's added on, and that happens to be the same dimension as the identity matrix. So we're just introducing those slack variables like I showed in the equation before. Then we're going to add another row down here to represent what our objective function is. And that's going to look like basically our value z minus c train, I suppose. So we're trying to maximize for z, and we'll bring across the coefficients there. And we'll add a 0 just to hold the place there. Over here, we're going to have our b like we had before, and then zeros to represent what we're trying to solve for by z minus ct. So that's a long and roundabout way of saying that we've taken this abstraction, this matrix math right here, ax equals b, and represented our constraint problem by adding in these other chunks. We've got the slack variables, the identity matrix, the objective function, and then some zeros just to kind of tie those down. But at the end of the day, this still looks a lot like ax equals b. And that's how we go about solving it, roughly speaking. So let's throw some examples of this. You know, at the end of the day, it turns out to be a lot like essentially a system of equations. We're going to have to handle a few things specially, and there's a lot of techniques for this. But conceptually, there's an important point. We speak of decomposition as a part of computational thinking. And the idea is to take a complex problem and break it down into smaller pieces that we can solve individually. So what I want to try to illustrate here is that we've taken optimization with this fairly complex constraints, and we've basically split it into different chunks, but then reassembled those back together into matrices that are in a very familiar format, something we know how to handle. So the problem gets transformed that way into a much simpler system of equations. The other point about this is that you can scale out. You know, rather than trying to solve for a lot of different variables and a lot of different constraints and a typical kind of very complex problem, now we're looking at a very familiar system of equations, linear algebra problem. You might have hundreds of variables or thousands of variables, and likewise, you know, that order of constraints. So this is a lot about being able to scale out to really large problems. As an aside, you know, I studied operations research a lot when I was an undergrad, and at the time, you know, my peers were looking at, you know, going into working for the Pentagon, working for Bell Labs, maybe becoming insurance actuaries. There weren't a lot of consumers in, say, the startup space for this kind of math. For what it's worth, I went up to Bell Labs, but what I've seen is over the past 10 years or so, there's much more appetite for these kind of optimization problems, and it's trickling down into smaller and smaller companies. We're getting smarter about how we handle optimization. But at the same time, there's going to be even more and more need for this once we get a lot of Internet of Things data rolling in. Okay, as a sidebar, George Danzig, I'd like to focus on him for a moment. He didn't exactly invent linear programming. There was a Russian author who really should be credited for that. But Danzig came out with the first paper and also had many, many significant contributions in the field. He's also the source of a rather popular urban legend. One day, George Danzig was in grad school at UC Berkeley. He was in Jerzy Neyman's math class, and he came in late to class. And he looked up on the board, and there were a couple of problems written up there, so he copied them down, thinking that they were the homework assignment. What he didn't know was that Jerzy Neyman had been presenting problems that hadn't been solvable yet. So George Danzig went and wrote these down, and you know, you can see the quote here. "A few days later, I apologized to Neyman for taking so long to do the homework. The problem seemed to be a little harder than usual. I asked him if he still wanted it. He told me to throw it on his desk. I did so reluctantly because his desk was covered with such a heap of papers that I feared my homework would be lost forever." And about 6 weeks later, one Sunday morning, basically Neyman is banging on the door, waking up George Danzig and his wife, and says, you know, basically he took the homework problem set and put an intro on it and got it published as a paper, because as it turned out, George Danzig had solved some previously unsolvable problems. Really amazing person. There's a great bio on him at Stanford. He had helped us set up the operations research program at Berkeley and then later at Stanford. Amazing contributions to the field. Now, let me get into a little bit of a case study here. Our foodbartender.io startup has a problem in terms of wanting to maximize net revenues, and we've seen some different rates of response amongst the customers for different categories of drinks. So they've done some analysis on how well their different categories of drinks are selling, and they've broken it down into 3 categories. There's the pre-prohibition drinks, very popular. There's some based on liquid nitrogen, which are also kind of picking up popularity. And then, of course, there's the ever popular freshly muddled drinks. So get those mint leaves in there and crush them. The problem is that sales were booked on a 5:3:2 ratio for net revenues in those 3 categories, at least over the last quarter. And now the company must adjust its sales strategy, trying to optimize for revenues next quarter. So we can define an objective function, z of x, and it's based on the x's, how much we intend to sell in the different categories. Those are the x's. And we've got a 5:3:2 ratio for the revenues that we've seen on those. So we can come up with an objective function that's basically taking that 5:3:2 ratio, and we'll create z of x equals 5:3:2, put some subscripts on there. So we're just going to take the data that we've had, our priors on that, and use that to create an objective function. That's how things are currently selling. Oh, and by the way, always have this constraint, because we can't sell negative drinks. Now, what we're going to try to do is optimize the revenue subject to our costs. In this business, there are 3 costs that are identified, 3 general categories of costs. One is having to pay for the ingredients, having to buy our local organic non-GMO ingredients for the cocktails. And another is the overhead for making those. Basically, the bartender salaries is the biggest component, but also just facilities for bartenders. And then thirdly, there's a matter of getting the mixed drinks out to the customers. So there's drone delivery. If you look at the table here, we've got a breakdown for each one of these different costs. We show what the ratio is amongst the different 3 categories of drinks, and also what the total cost is in the last quarter. So we come up with this system of constraints here, where we've got x0 plus x1 plus 3x2. Okay, and this is for the ingredients less than or equal to 100,000 last quarter. So 113 as far as our ratio of the coefficients. Next one, bartender overhead was 10. Let's see, 4. Oops. And what is it? 5. Okay. So this is a pretty significant overhead. Obviously, your salaries are going to be probably pretty big. Component. So we've got a 10-4-5 ratio, overall $600,000 last quarter for bartenders. And then the last one is x0 plus x1 plus 3x2 less than or equal to 150. And so actually the cost of delivery are the last line here. So if you look at this, then we can break this down into our vector of our objective functions coefficients there, a vector C. We've got the constraints here. We've got our coefficient matrix for the different variables. And from that, we can start to put all the pieces together and build this out into a linear programming problem. So show the transition there from the equations down to the matrices, down to basically assembling all the parts into something that looks familiar. It's a system of linear equations. Now I'm going to show an example of how to solve this. It's based on, ultimately it's based on a mathematical programming language called AMPL. And if you want to check it out, there's a free book about it online. Some great examples in there. There's an open source package called GLPK. It's GNU Linear Programming. And there's some great resources there, but it's essentially it's a wrapper around AMPL. Has a lot of great examples, though. I definitely recommend checking out the example models that are implemented. And then over the top of that, there's a Python wrapper, PyGLPK. And I've got it installed. I will say that it could probably stand a little bit more updates. There's been some problems with it on the Macs, the later versions. But just to take a look at what a Python interface like this would be, we're going to import GLPK. Got that up there. And we set up a model, create a class, give it a name. We say we're going to maximize the objective function. We've got the rows. Row names are corresponding to the different types of constraints here. So we've got ingredients, bartender, and delivery. I should have put these down. Bartender and delivery. And so we set that up into the model, add the different bounds on them, the constraints, and then we set up the columns and populate all the values there. But then at the last line, we say lp.simplex. We call simplex method on this. And it goes out and finds a solution, or tries to, and then prints out the results. If you have any problems with Python GLPK, if there's any issues during installation or compiling, as an alternative, you could just use GLPK directly, use the GNU package. It's a little bit easier to install in some ways. And essentially the Python app that I showed generates the GLPK model anyway, so it's the same results. But if you want to take a look, let me go ahead and run this one. Okay, I've got a model that's built out in GLPK, and it's in the GitHub directory. It's ch5_lp.mod. And it's pretty simple the way this is set up. There's 3 variables, x0, x1, x2, just like we have up here. And they're all set to constraints. That is to say, they're all greater than or equal to 0. And then the next part, we state the objective function. We say we want to maximize the value of 5x0 plus 3x1 plus 2x2, which is what we've got up here. We're going to say it's subject to some constraints. We've got the ingredients row defined here, the bartender row here, and the delivery row here. And then just give it an end. When we run that, GLPK is actually called by using a solver. GLPSol is the name of the package. And you say you're going to provide a math module, this linear programming module that I've defined up here. Hit return, blam. So it comes back and it says, okay, it read all 16 lines of the input model, and then it generated the matrices for the objective function, the different constraints. Starts to go on simplex method. Original linear program has 4 rows, 3 columns, 12 non-zeros. And then they simplify that down, 3 rows, 3 columns, 9 non-zeros. Go through all the motions of finding a solution and get down to the point. It says crashing, but ignore that. It's not actually the computer crashing. It's their terminology. We get down to the point of where we have a feasible solution. And there we go. Objective equals 3.67 and change. Yeah, actually, so it's the same thing I've captured up here. And if you'd use the Python, it does the same thing. It's just that this kind of Python relies on some C under the hood, and the later versions of Macs are having a little problem with C compilers. Okay, so this is interesting. We've got Z equals 367,000. That's the net revenue that we're trying to optimize. So that's the projection. And that's based on a sales target for pre-prohibition drinks, X0, at 3.3 0.33, which turns out to be, if you multiply here, it'll be 167,000. Liquid nitrogen drinks, X1, come out to 66.67. If you multiply times the coefficient, you get 200,000. And then freshly muddled drinks, X2, come out to 0. So the optimal model comes out where that variable is tied to 0. So we're not going to have any revenue on that. Basically, we're going to blow it off. So to maximize net revenues next quarter, FoodBarTender.io needs to ditch the freshly muddled drinks. As it turns out, they're expensive to deliver. If you drill down in the model and you look at the coefficients, you'll find out that it's actually the delivery costs were really constraining freshly muddled of making any revenue. So the optimal thing would just be to ditch that line altogether and focus on the other two product lines. The sales targets are basically, 1/3 of the mix is going to be pre-prohibition and 2/3 of the mix are going to be liquid nitrogen. And so the company is going to look towards 367,000 in net revenues on approximately 800. But the total cost was 850,000. Total revenue, of course, would be combine that part, those two parts. Overall, you would anticipate a 30% operating margin, roughly speaking, which is not bad. Okay, another sidebar, I'd like to focus in on Pedro Domingo's professor at University of Washington and expert in machine learning. Actually, Pedro Domingos has a MOOC online about machine learning. It's quite good. There's a paper that he did in 2012. It's called A Few Useful Things to Know About Machine Learning. And I highly recommend this. When we talk about machine learning, really it's a subset of optimization. The hard work that you're doing in machine learning is optimization. And there's a lot of different techniques in machine learning. They've come out of a number of different fields, some from signal processing, some from biology, some from hard AI, symbolic logic, others from like text document retrieval. A lot of different fields have come together and contributed different types of techniques and algorithms, etc., different ways of evaluating how good or how bad your machine learning algorithm is running. And the problem there is these different camps have a lot of different nomenclature. The people who do signal processing speak in a very different language than the biologists, and a very different language from there than, say, the people doing, library science and information retrieval. Completely different fields. So one of the problems that I've seen with machine learning over the years is it's a little bit unapproachable because it seems very ad hoc. It's hard to understand that there's all these different languages being used to describe essentially the same problem over and over in different fields. So this paper from Pedro Domingos tries to take that to task and shows machine learning as, like I say, a subset of optimization. You're trying to generalize from a large amount of data, trying to generalize learnings about particular patterns. We can call those classifiers. To be able to predict some kind of outcomes in the future. So the paper here breaks down almost all of machine learning into a set of categories based on really 3 points. There's representation, evaluation, and optimization. Number one is you want to be able to state your problem in a way that's calculable. You want to represent. So, say you've got, you're trying to optimize sales conversions off of sales leads. That might end up being a graph problem, actually, in a lot of ways. And so that's a kind of representation. Evaluation is where when you're training different types of classifiers, generalizing different types of patterns, you want to be able to distinguish the good classifiers from the bad ones. And then optimization is where if you've got a lot of classifiers possibly trained, you want to pick out where is really the highest scoring one. Again, this optimization problem, there's n variables but less than n equations, if you will. So there's not enough data, so there's too many possible solutions. You want to optimize, you want to pick the best ones. And that's where machine learning really is tied in deeply to optimization. I can try and illustrate another point about here that Pedro Domingos makes very well. So I'll try to draw some dartboards. Let's see if I've got this right. Okay, Gonna draw a dartboard. I'm not exactly the best darts player, but I'll take one for the team here. Okay. Not sure which is better or worse, my drawing dartboards or actually throwing darts, but they're both fun. Okay, let's see here. If you want to throw some darts, now, if you have a really bad dart thrower, you might be all over the map. Maybe, well, let's say we don't even catch the center. Okay, there's all kinds of darts thrown all over the board. Now, you could have a case where you've got somebody who's pretty good at throwing darts, but just always a little bit off the mark. So they've got a tight cluster here, blam, 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 but it's not quite hitting the bullseye. And there's another case where you've got somebody who's, better, but they're kind of spread out. They're maybe hitting the mark a little bit, but a bit spread out. Certainly better than all over the board. And then you've got the case where you've got, just experts, Olympic competition dart throwing, where they just hit the bullseye. One of the points that Pedro Domingos makes about machine learning is that you're struggling with a kind of trade-off. In the worst case, you don't really recognize anything. So it's kind of like me at a dartboard where you're just throwing all over, hitting all parts of the board, except for probably the bullseye. Now that's worst case scenario, and hopefully machine learning techniques are well beyond that. But you could have the case where you've got what we call bias being introduced. And so here, let's see, we'll say that this is bias. And then here is variance. So if you've got some bias, you've got low variance up here, but you've got high bias. That means that you're throwing a nice tight cluster of darts, but they're just always sort of off the mark. Up here, of course, you have a case where you've got high bias and high variance. And then down here, you've got the case where you're just hitting the bullseye all the time. In machine learning, you're not going to do this. Okay, there's the idea of something called no free lunch. You're going to have outliers. You're going to have overfitting. You're going to have different types of issues introduced. There's no perfect set of classifiers that are going to solve all the problems. So you can just count this part out. The question is then making the trade-off between bias and variance. And certain ways of training classifiers are going to, with a given set of data, are going to lean more towards bias or lean more towards variance. And that may be useful in a business setting. So, for instance, if you're training an anti-fraud classifier for e-commerce, one of the trade-offs there is if you've got a lot of false positives, say with your customer base, you're going to introduce a lot more cost for support. If you start shutting down valid customers on valid transactions, they're going to call up and they're going to want customer support to fix the problem. On the other hand, if you introduce a lot of false negatives, then you get in trouble with the bank because you get a lot more fraud that's coming through. Customers will be more happy, but so will the fraudsters. So what I want to point out is that in certain types of circumstances, you can make trade-offs between how you're training and which direction here you're leaning. Where do you want to take advantage of more or less variance, depending on what the business case is. I've definitely seen the case where the finance people wanted to eat the cost of customer support for a while just so they could get in the good graces of the bank because they had a lot of fraud rate going on for a while. And once they got that cleared up at the bank and the bank signed off on it, then they could go ahead and change the models so they eased back off on the customers. But I want to make the point that there's no free lunch. You can't get a perfect one. And you're always struggling with trying to get some sort of trade-off here. Pushing this a little bit further, there's a professor at Stanford in EE, Stephen Boyd, also Neil Parikh and others working on that team, but it's the Information Systems Lab at Stanford. They came out with a paper 2011 called Alternating Direction Method of Multipliers, ADMM. And this is an example. There are others. This is a great example proving the point that there is kind of a general rubric for machine learning, and it really is about optimization. What ADMM is saying is they've got a couple of equations or rather they've got one linear system there. Okay, what this is saying is we want to minimize this objective function here. We've got f of x plus g of z, and we want to minimize that. Looks a lot like the linear programming we had before. Subject to down here, we've got ax plus bz equals c. So subject to some constraints. To translate, we've got f of x being something called a loss function. And we've got g of z being something called a regularization term. So we've got a constraint problem here. It looks a lot like the linear programming that we were working with just recently for foobartender.io. But the point that Boyd and his team is making off of ADMM is that they can take a lot of different types of machine learning and essentially generate them out of this set of equations. In a way, they're turning parts of machine learning into more and more of a compiler problem. The idea is that, if you have a lot of data, you can sample out of that. You can test some different approaches to it. Essentially, it's a compiler optimization to choose what kind of algorithm and what kind of parameters you're going to use. Maybe this is not exactly in production yet. This is a research topic. But you're seeing things like MLBase out of Berkeley on top of Spark, which are looking towards implementing things very much like this or along these lines. So the quote is, many such problems can be posed in the framework of convex optimization, like we were talking about with linear programming. Given the significant work on decomposition methods and decentralized algorithms in the optimization community, it's natural to look at parallel optimization algorithms as a mechanism for solving large-scale statistical tasks. In other words, yeah, we're working with big data. This approach also has the benefit that one algorithm could be flexible enough to solve many problems. That is to say, one constraint problem, one optimization problem can represent, whether you're using logistic regression or support vectors or, random forest or different types of algorithms. It can all fit into this, and basically it's a matter of changing the parameters around. Also, I want to point out that these two terms here, the loss function, the regularization term, this show up over and over again. When we go back to the dartboard, the loss function is really about the variance. How tight are you throwing the darts? And the regularization term is, where you're going to try to avoid overfitting. You're going to try to avoid the bias. So this is a very general approach towards machine learning, and it really is saying, look, it's subcategory out of optimization. There's a few great books that I'd recommend. There's actually a lot, but I wanted to pick out enough that would fit on the screen here. So Stephen Boyd and Levin Vandenberg have convex optimization that has a lot of these subjects covered in detail, and I find it's a relatively accessible book as well. We talked about AMPL as a modeling language for mathematical programming. When I was showing the linear programming problem, GLPK, it's really using AMPL under the hood, as are a lot of other different types of solvers. And I should make a point that when we talk about mathematical programming, we mean that in a slightly different sense than, say, computer programming. Okay, we're not talking about like C++ programming or PHP programming or SQL programming. We're talking about mathematical programming in terms of how do you frame the problem into something that you can solve with a method like linear programming. Sometimes linear programming isn't going to work. The problem just doesn't fit. So there's other things like dynamic programming. But they all kind of fit in this general umbrella category of mathematical programming. You might notice one of the authors on that book is Brian Kernighan. Those of you who are familiar with Unix and the C language might recognize that name. Also, going back to the basics, this third book, Linear Programming and Extensions by George Danzig from 1963, really that's what kicked off a lot of it. If you want to go back to the original sources, he was actually writing papers much earlier than that, but that's a great book.